Great, thanks Pedro. Hello everyone. I feel like we have a universe to cover at about 25 minutes, but let's start, I think, with a telescope that got mentioned in several of the talks, but which we didn't focus on, which is the JWST, which is our new toy. And Jake, this is your go-to instrument. Tell us a little bit about what it is and what it can do for exoplanets.
Yeah, if I could drive, it'd be my car. Once I use it. But before I mention James Webb, so both Suzanne and Jane give a bit of their background into astrophysics, so I'll do the same. When I grew up, my family and I would watch Red Dwarf. We weren't really a Star Trek family, so it was mainly Red Dwarf, a bit of X-Files, and that really got me into it. And then I did astrophysics at undergrad, and then the rest is history. And now I'm here, and I use the James Webb Space Telescope. It was launched on Christmas Day, and I was alone in Montreal because it was COVID, and I couldn't come back to the UK. But it was a happy Christmas because it didn't mess up. It's up there, so we're happy. And we got the first observations, science observations, in 2022, and people tend to think that astrophysics is quite a slow-paced research field, but with the launch of the telescope, it was kind of crazy. So if anyone here knows about Slack, like the messaging work service, we, maybe 100 of us scientists were on Slack, and someone posted the first data set. And we all rushed and scrambled and tried to figure out what's in the atmosphere, what's going on, what can we do? And it was interesting, we saw this weird bump in the data that was shown, what Jane did show.
So this is looking at the atmosphere of a planet.
Right, so in the transmission spectrum that Jane showed earlier, there was a big CO2 feature that we saw, and then we saw some bumps from water, but next to the CO2 bump, there was a tiny other bump that was visible in multiple different observations. We were like, what the hell is this? Like, this was never predicted in any of our models before we launched the telescope. And it turned out, after frantically running models, people running new bespoke chemistry models and all these sort of things, we figured out it was SO2, sulfur dioxide. So it was the first ever hints of photochemistry in these atmospheres. And so the first ever observation, we found out that exoplanets also have photochemistry, just like Earth's atmosphere. So that was pretty cool.
Yeah. So what is it about JWST that makes it special? We heard about what we can do from the ground, we heard about these discovery instruments like Corot and TESS and so on. So what is it about JWST that makes it so powerful, that makes people like you go mad spending months applying for time on it? The whole department goes crazy for a couple of months as people try and write their proposals to use JWST. So why is it so valued? What can it do that others can't?
So it's the first purpose-built space instrument that's able to look at atmospheres of exoplanets. So the design in mind, one of the instruments, was to exactly do this. Before that, we had things like the Hubble Space Telescope, but it wasn't purpose-built. So we were trying to use, a spectrograph on Hubble that covers one of the water bands, but it wasn't, our ideal scenario. We had to develop techniques that could better figure out what the signal was. So we had this complete wavelength coverage that we'd never had access to before. Previous telescopes like Hubble or Spitzer, they would cover tiny portions of the transmission spectrum that would only look at small wavelength coverages. But with James Webb, we can now get a 0.6 to 12 micron beautiful spectrum that covers multiple different carbon-bearing and oxygen-bearing species, where we can do these chemical inventories. We also cover ranges that can look at clouds and other things like this, so we could get in a rich chemistry.
And one of the things that's come out of these observations and others, I think, is the effect of the star on the planet, which is something we have to consider as well. Suzanne, do you want to tell us a bit about, we sort of touched on it in the talks, but we have to worry about the environment the planet finds itself in as well, right?
Yeah, absolutely. So we think, because it's also partly because the planets that we can find and study most effectively orbit quite close to their host star. So their entire energy budget over their lifetime is completely dominated by what they receive from the star. But most importantly, the radiation falling onto their atmosphere can very readily strip some of that atmosphere away. particularly when it's an atmosphere that's made of light gases like hydrogen and helium. And in some of the plots I showed, you saw that there was a significant gap between these planets with sizes up to Uranus and planets which are larger than Saturn. And if you look close to the host star, there's actually what we call the Neptune desert at very short periods. And this is because we think that anything that was the size and mass of Neptune in that region would have lost its atmosphere and would have become more like a super Earth or a smaller planet with a very small, more tenuous atmosphere. So that's one of the ways in which the influence of the star is very important. The other, as Jake just mentioned, is photochemistry. So the incident radiation from the star drives chemical reaction pathways in the upper atmospheres of these planets that cause species to exist that wouldn't exist otherwise and change the chemical balance of the atmosphere. Another one is the interaction between the star and the planet, magnetic interaction, which we alluded to after my talk. There is also tidal interaction, which we talked about. So this is where the planet raises tides in the star raises tides in the planet, and that causes the synchronization of the planet. So we always have the same side facing the star. It also means that the planets on shorter orbits tend to be in circular orbits, whereas planets further out can have more elliptical orbits. And finally, there is this consideration that what's happening on the star affects our observations of the planets, because the observations are always indirect. So I talked about how the variability of the star in photometry makes it hard for us to find the transits, and in radio velocity too. But the star spots also affect the spectra that we get for exoplanets, and the way in which they change, we have to take that into account too.
Yeah, so one of the really annoying things, as someone who doesn't want to model stars, is these star spots, if they're on these colder stars, so these M stars, the star spots could have water vapor in them, and that could then imprint itself onto the planet spectrum. So it could masquerade as
so that's a star with water vapor in its atmosphere.
Yeah, within the star spot.
Yeah.
And that could then masquerade as a signal from the planet, and then we could tricked into believing that the planet has water vapor, but it's actually from the star spot that we haven't modeled correctly. And that can be quite tricky when we try to look for water as a biosignature on terrestrial planets around these stars.
And I saw some frowning in the audience when you said that water vapor can exist in star spots, but we actually have observed sunspots on the sun where CO molecules have been seen, and that was actually an observation first made in Oxford.
Right.
First interpreted in Oxford.
And these small dwarfs, the temperature in their atmosphere, even though they're stars, is a few thousand degrees maybe? Something like
so that also has quite a big impact. So the energy that the planet is receiving and the colour of light that the planet receives differs. So for the sun, we sort of have this peak sort of around, I know it looks yellow, but sort of peaks in the green wavelengths. And then for the smaller stars, like Proxima Centauri, the nearest star to us, is a red star. So these M dwarfs make up somewhere between 70 and 80% of all stars in our galaxy and probably throughout the universe.
And M dwarfs are just small red dwarfs.
They're just small red dwarfs. So they're about a tenth of the size of our sun. And most of the nearby stars to us are M dwarfs as well. And so the peak of their energy that they give out to the planet actually peaks in the redder wavelengths. So you can imagine if you're a plant trying to photosynthesize, your chlorophyll that you use is actually, unsurprisingly, perfectly suited to absorbing the light from the sun. So there have been ideas put forward that plants on planets around M dwarfs could still use chlorophyll, but there's another type of it that actually has absorption over in the red and the infrared wavelengths. And so those plants would actually look purple to us.
As seen on Star Trek, of course.
As seen on Star Trek,
But this is an example of where this chain of logic goes. If you start thinking about looking for biosignatures, people have proposed something called the red edge, which is a feature in the spectrum where the plants are absorbing the light. You might see that, but presumably if you've got alien plants with different chlorophyll, you have to think differently about biosignatures.
So the spectral features might get shifted depending on what you're looking for.
I was going to ask about you talked a bit about looking for life actually, when we're talking about the effect of the star on the planets. How do we take that into consideration when we're thinking about which planets might be homes for our kind of life?
Yeah, so assuming the atmosphere survives, I think if we want surface life, we probably need an atmosphere. We would like a magnetic field Not all the planets in our solar system have magnetic fields. We do, and what that does is that shields us from a lot of the harmful radiation from the sun. So all these charged particles, they sort of get funneled through our magnetic field. So when you see the aurora borealis, the northern or southern lights, or aurora australis, that's our planetary defense shield in action. Okay, that's protecting us from harmful flares from the sun. And it turns out our sun is actually on the quiet side. So this is one of the outcomes from the Kepler mission, actually, that stars like the sun are actually about 20% more active, I think.
There's this long argument about whether the sun is more active than average as well, right?
Yes.
But sun-like stars, have more flares. So
and
it's more sunspots, more flares, more activity.
more flares. And so as you go to the cooler stars, which are our best targets, because there's lots of them and they're easier to do, all the ratios are better, they actually flare a lot more. And so that might actually be damaging. So you could have a flare, for example, for Proxima Centauri, it flares every 6-ish days. And even if there was a magnetic field, that protective field might get squished all the way down to the surface. So anything that it might be protecting on the surface might get damaged by it. So you can then start to invoke other things. People have written papers about using bioluminescence to try and counter that sort of harmful radiation coming in. You see this on sea turtles, and in the ocean you can see little algae luminescing. If you rush up the water, they sort of glow. So life could potentially be extremely adaptable. That's what we don't know. So that's why we have to be very open-minded when we look for sites for life.
Yeah.
And one thing I want to mention is, so rocky planets around these M stars, these cold stars, we actually don't know if they have retained atmospheres, and it's one of the biggest questions right now using the James Webb Space Telescope. We've actually used over 100,000 hours observing time looking at these rocky planets around M stars to try and figure out, do they have atmospheres, can they retain atmospheres in light of all this activity, because they are right now our best option to potentially look for habitable planets.
So let's do a bit of meet the neighbours, I think. If we're talking about these particular planets that we're spending this time on, there were results recently from a system called the TRAPPIST system. Do you want to, Jake, maybe tell us about one or two of the nearby systems that you and others are putting effort into studying?
Well, I can do TRAPPIST.
Yeah, sure.
So when I was in
Montreal... The
Montreal...
planet is named after the beer, by the way. So,
yeah. So TRAPPIST, fun fact, my interview for my DPhil in Oxford was the day when the 7 TRAPPIST planets were announced. That was a bit of an exciting time. When I moved to Montreal, I joined the NIRISS team. NIRISS is an instrument on board James Webb, and the NIRISS team, they had guaranteed observations of the TRAPPIST system. And so we've looked at planets B, C, D, E.
Maybe just say how many planets.
We've looked at the 7 planets.
There are 7 planets.
There are 7 planets around this system, and they're all Earth-sized-ish.
But close to their stars.
But very close to their star. To the point where planet E, which is the most habitable one, it's in the smack bang in the middle of its habitable zone around its star. We think that's our best chance to find life or find biosignatures or an atmosphere around these planets. A paper came out, I think, maybe a couple of weeks ago, unfortunately showing that we don't see an atmosphere yet, but we do have about 20 more observations to go, so it was just an initial look. So it's still an exciting system to look at.
And how far away is it?
I think it's maybe 15 parsecs, maybe?
Yeah,
40 light years.
40 light years, so it's nearby, basically.
And that planet E, it goes round the star in how many days? It's very few, right? Because the star is tiny. The star is a tenth of the size of the sun.
Yeah, I think it's something maybe 20-ish, maybe a bit more days. It's very, very rapid.
There's a fun fact about how the masses of these planets were measured. So they are in what we call a resonant chain. So I can't remember exactly what the ratios are, but when planet A goes round once, planet B goes round, it's actually 2 to 3, and then 3 to 5, and then 5 to 7, etc. So, and that means that they have every orbit or every few orbits, they come quite close to each other and they tug on each other. It means if you're observing the transits, they come slightly early or slightly late. And
just from the gravity of the other planets.
Exactly.
Yeah.
And by observing multiple transits of each of the planets, you can actually infer the masses of all the planets. And this is how we know the masses of those particular planets. It's a really powerful technique for the systems we can apply it to.
Is that because you can't do it at radial velocity? Or?
So there are also radial velocity constraints on the masses,
That's from the pull on the star.
That's from the pull on the star, but it's a really complex one because there are so many planets, and the star it's not especially quiet, it's not especially active either, but it does vary, and it's really red and quite faint, which makes it hard to measure the radial velocity signal.
So this brings us on to something I wanted to get out of you, Suzanne. It's very obvious working with you in your talk that you may be an exoplanet person, but you're also a stellar person, and that's true of almost everyone in the field. Can we say something about how we might advance our understanding of the stars so that we can know the planets better?
Yes, I mean, you could probably sell every single experiment to study exoplanet as an experiment to learn about stars. Partly because we find and study exoplanets by observing the stars, so necessarily we learn things about them, but also, as I discussed, because we need to understand the stars extremely well to find the planetary signals. One of the things that I spend much of my time worrying about is all the different flows that are going on in the atmospheres of stars, because when we're measuring the velocity of a star, we're measuring an average over all the flows that are going on its surface. And I don't know if you can remember now, but when I was showing a zoom into these star spots, if the eagle-eyed among you might have seen that there are also this mottled pattern on the surface of the star away from the spots. And if you zoom into that, you see that it's a pattern of convection cells, essentially bubbles of rising and falling material. So hot material rises from below. It's basically boiling. It's
soup boiling.
It's plasma boiling, but yes. So we have hot material welling up, and it's bright, and we have cool material falling down, and it's cold. That's called granulation, this pattern. And then it gets disrupted by other things like magnetic fields. And actually, these two processes, convection and magnetic fields, are some of the least understood problems in all of astrophysics. So by studying the stars, in order to find the planets, we're also learning about how these processes manifest in the surfaces of stars in great detail.
And Jane, what about when you get to the extremely large telescope? Can we learn more about these processes, or do they become? Do you not worry about them because you've got the resolution? Do they become more of a problem?
So I think at the moment, in terms of detecting planets and how the stars impact that, I think that is actually driven by trying to understand these problems and remove those effects from your radial velocity measurements. So it's not a case at this point of having a bigger telescope is going to fix that. You'll get more photons, but you'll still have to fight the stellar activity. But in terms of sort of the stellar astrophysics, I think one of the fun things at the moment is looking at the interaction of the planet and the star in terms of their tides, and how the planet can sort of raise this tide on the star. And it allows you to actually try to understand the internal structure of what's going on in the star, and you can do that as a function of stellar temperature.
Excellent. I'm going to do 2 quick-fire questions, and then we've just got a bit of time to come to the audience. So if you could be thinking of any questions about anything you've heard today that you'd like to ask, that would be good. One thing I want to get across is the diversity of things that you all do in your exoplanet work. And Pedro said that we should be talking about what's happening now. So I'd like to know what was the last paper that your name appeared on that came out. And Jake looks like he remembers his, so we'll go with Jake.
So I actually published a paper earlier this year using James Webb data studying one of these super Earths, but it was around a quiet M star. So we believe that it was out of the population of M stars, it has the least activity. And so our idea is if it has this activity, maybe the planet has attained an atmosphere, or it spent most of its time in a regime where there was low activity and it could replenish from whatever was in, let's say, the molten surface. So we published that, and we didn't detect an atmosphere, but we're hoping that if we get more data in the future, we will be able to.
And science is sometimes about not detecting things. That's fine. Suzanne?
So actually, pretty much the last 4 papers that my group's been involved in were all to do with observing the sun as though it was a different star. This is something that we've been doing for the last 10 years to try and understand how the spectrum of the sun changes over time due to all these phenomena, the star spots, and the granulation and all these other things. And we use it as a test bed to develop and test mainly machine learning algorithms to understand these variations well enough to find planetary signals. The nice thing is the sun is the only star that doesn't have planets if we take them all away. Whereas any other star we look at, we never know if there might be a planet that we just don't know about yet. So we can take the sun. What we do is we put the light from the sun through a very small integrating sphere, and then we feed it through an optical fiber to the same spectrograph that we use at night to observe distant stars. And actually, the observatories are very amenable to this because it doesn't cost them any time, right? The telescope is not being used during the day. And we now have these exquisite 10-year data sets that we can use to test all these different methods. And so that's what all the recent papers that I can think of.
Very good. Jane?
Yeah, we had one this week, actually.
Good.
This was Ben Sutcliffe, who's a postdoc in Edinburgh now, who was a graduate student with me when I was in Amsterdam. And this was working on, I showed about trying to map planets, and this is sort of doing the groundwork now to prepare to be able to use that on the ELT. So we used the Large Binocular Telescope, it's about an 8-meter class telescope in Arizona. Texas?
Yeah,
Arizona. Texas, yeah. And we actually looked at a system that was sort of, it's a star that has what sometimes gets called a planetary mass companion. And what that means is we don't quite know whether it's a planet, whether it's a brown dwarf, whether it's a small star, but it's smaller than the star that's there. And the idea that we're trying to do is actually remove the starlight, isolate the planet itself, and make a light curve of that planet. So we're trying to watch how the brightness of the planet itself, so not the star, but the planet. And so instead of seeing star spots rotating in and out of view, we're looking for either things like Jupiter's Great Red Spot rotating in and out of view. And what that would do is instead of having this sort of nice flat light curve, you'd have this very sinusoidal shape as the
Like
storm.
it's just brightness versus time.
Yeah,
right,
yeah. Or what I really want to do is to watch the planet and see if we have any transiting moons pass in front of it. So exomoons, they must surely exist because they're around every giant planet we have in the solar system. They must be out there, but they're so hard to detect that we haven't found any yet. But I think this is like we're so close to the edge of doing this. I think it's got to happen.
First
soon.
exomoon.
Yeah.
Soon. Good.
Yep.
Really quick fire question. Part of the reason for doing exoplanets today for this, our first afternoon, was that, as you heard, it's 30 years since that first detection of a planet around a normal star. So let's do the normal panel thing and go forward 30 years. We'll be on our about 100th afternoon of astrophysics. I think, Jake, you'll probably still be here. What will be the big unknown in 30 years' time? So we'll solve many of these problems. What's the thing you'll sit here in 30 years' time and say, the thing we're working on now is, I'm going to start with Jane.
Oh, gosh. I think there's going to be a huge amount of change in the next decade in terms of what we do know about exoplanets. So I think there's the biosignature survey. So what does it mean if we don't find anything? I think if we find a clear signature, okay, life. But if we don't find it, does that mean life is rare or not? And that becomes a numbers game. We have to look at a lot of planets to try and figure out if life is rare.
Fine. Suzanne?
Yeah, I think, we have two alternate universes that we might find ourselves in. Either we will have found clear evidence for biological activity on another planet. If we find it in the first decade of searching, as this would be, then it means it must be ubiquitous. Whereas if we don't find it, it might be a sort of longer and more complex process to understand exactly what the limitations are.
Because we will have looked at tens of stars, or tens of systems.
Yeah, we will have looked at a few tens.
Okay, so life, Jake?
Studying the atmospheres of exomoons.
Oh, nice. Okay.
Yeah.
Is there a Titan out, an exotitan or something out there?
The Pandora, have you seen an Avatar movie?
Fine.
It's based on a real star system. So,
And there's a candidate, right?
and it's a candidate for a moon. So
Good. Okay, well, we've done Red Dwarf and Star Trek to Avatar, so this is good. At this point, we've probably got about 5 minutes for questions, if there are. If you're online, you can ask questions via the Q&A, and they'll get relayed to us. But let's start there. There's a microphone coming towards you.
Thank you so much, everybody. First of all, just a quick question about how the telescope time is allocated, because we know James Webb, of course, has other major things to do. So
yeah, people like me sometimes want to look at galaxies.
So how much time is spent for exoplanets, and how do you persuade the people who decide that your research is more important than the other people's?
Yeah, I'm going to let Jake answer this.
This is a really great question, and so we just went through the process recently. So essentially what you have to do is you have to sell your case. So you write a science program, a proposal, that would say, okay, I want to answer this question, I need X amount of hours, and the deliverable will be this thing. And by the amount of proposal pressure there is, that's how they allocate the distribution of the different subfields. So exoplanets tends to get 1/3 of time using James Webb. It's just because it's such a new field, there's so much to do and look at, and there's so many of us wanting to do different science that there's a lot of pressure to try and get time, and it ends up being about 1 in 10 of the proposals get selected, so it's still quite difficult to get telescope time.
And most of those rejected proposals are great. So we could easily fill up 6, 7, 8 JWSTs worth of time with good science.
Every year.
I just wanted to bring up an interesting sociological fact, which is that about 5 years ago, maybe, for these really prestigious and important observatories that everybody wanted time on, we switched to an anonymized format of proposals. So before that, we applied as ourselves, and unavoidably it's also our peers who review the proposals, and the knowledge of the person applying influences what you think of the proposal. And so now when we apply, we have to make it completely anonymous. And in fact, if we reveal our identity, even inadvertently, in the proposal, we're disqualified. And this has led to a great change in gender equality among the proposers, and also an increase in the number of young researchers getting time, which is good on both fronts.
Good. Any more questions? Yeah, just over here. I like making microphone runners run, so we're going to come back over here for a question next if there is one. But yeah, good.
Thanks. One important question is, how vulnerable is life on planets such as ours? And I just want to pick up one of the graphs that I think Jane showed of the concentration of oxygen in the Earth's atmosphere, which I guess the data for which must come from ice cores. I guess
yes.
It must. But there was one point where oxygen dropped to 0, and then it picked up again.
I know, I saw that last night as well, and I spent quite a bit of time reading around what was going on.
The question is, does that indicate some sort of mass extinction that we're not aware of, or can it be tied up with something?
So it's a good question. So the actual measurements of the oxygen, I think, come from what the chromium isotopes are doing. And yeah, I guess they go and dig cores down in the Arctic, Antarctica, and see what's going on. And so I was following the reference trail for this thing. It was about 1.9 billion years ago that you had sort of the great oxidation event, the rise from the cyanobacteria, and then, it suddenly dropped off. That period of rise and then fall, the in-between bit was a snowball Earth phase. So the Earth got much colder and essentially iced over. And I don't know if that led to a reduction of maybe the sort of oxygen just falling out of the atmosphere. Does it make sense?
I think it's the activity is trapped in the ocean under the ice, so the atmosphere loses its oxygen. So I think that's right. Yeah.
Yeah. So you get a drop, but then it thawed, and then the cyanobacteria picked back up again, and so then you get the oxygen back.
But the general point about vulnerability, I mean, you made a point of saying exoplanets change over time on all these timescales. Presumably, life changes on timescales.
Yeah. So very early life didn't use oxygen; it used hydrogen and sulfur as its compounds for doing all its metabolism, and now we use a lot more oxygen. And so life on Earth seems to be very robust in the sense that it's always survived, not always in the same form as individuals, but life persists. So I think if life can get a foothold, then perhaps it can hang on.
Good, we've reached my childhood in Jurassic Park, where life finds a way. Suzanne?
Yeah, I mean, picking up on that, the conditions under which life has flourished and diversified on Earth have changed a lot through the lifetime of the Earth. The brightness of the sun has doubled since life appeared, but the surface temperature of the Earth has barely changed, and that is because there is life on it. So you can think in some ways of life as a stabilizing or adaptation mechanism, and if you want to think in very generic terms, all of the physical processes that occur, you could, it's oversimplifying, and my colleagues will probably argue with me over this, but you could think of them as mechanisms for producing entropy at the fastest possible rate. And life is amazingly good at this. And so some people would argue, just from that simple argument, that any planet that could potentially support anything like life will develop it for that reason. We have no evidence for that, or nor we as physicists, we actually want to understand the detailed mechanisms by which this would happen. But so yes, there are lots of things that can threaten life. I wouldn't be at all surprised if there were lots of places where something like life develops and doesn't really get started. It may be very hard to tell for us as remote observers. Because, it's one thing to look for signs of life on another planet. It's another to look for all the life that doesn't produce remotely observable signatures.
Yeah, and you can see why we need our interdisciplinary conversations with earth scientists and life scientists and so on. So this is where this subject really broadens out. I will take one more question, if there is one. Good. Next to the microphone. Good.
Thank you very much. You're building all these fancy new telescopes that are on the ground, they're great and fantastic, but what sort of problems do you have with things like all these Starlink satellites and all this space debris sort of coming up? Are they going to impact your observations?
Yeah, do you want to?
Suzanne?
So Starlink and satellite clusters are very problematic for ground-based astronomy in general. We are not the part of the astrophysics community that is perhaps most directly impacted by it, because we tend to look at bright things compared to most other astronomers. But it is pretty catastrophic for some other area. Space debris is also problematic, and we have to worry about it. But again, a lot of the telescopes we were talking about, like JWST and like PLATO, are actually going to this second Lagrangian point of the Sun system, so they're actually quite far from the Earth. So if they make it through the debris, after that they're fine.
And that's not too crowded yet. Thank you for that question. Thank you for all the questions. It's been great to have you here. Pedro, am I handing back to you? Apparently so. Good. Well, please, let's thank our panellists.